Alright, here we go. Shout out to all those chemistry kids who are trying to cram it in at the last second. This is day 5 on predicting products. We're going to go over the review sheet here. This first page is not actually on the review sheet. This is a summary thing we did on the first day of notes where we wrote down the 5 basic combinations for our reactions. We have our double replacement where we have 2 compounds, something with a positive charge. We have a compound with a positive charge. A would be positive, B would be a negative. So we might have like potassium and chlorine, or we might have aluminum and nitrate, something with a positive and negative. And then you have the other compound, which is also a combination of positives and negatives. And we are switching the elements around so that we're putting them in new combinations of positives and negatives. And then we have the single replacement. With single replacement, we have a compound that's positive and negative, and we have a single element all by itself. That single element is going to try to replace one of these two in the compound. And in order for us to figure out whether or not it can replace them, we're going to have to see if it's higher on that activity series, which is on the back of your periodic table. And so for those two reactions, on a couple of the questions on the test, you are going to have to predict what's in the box. You're going to have to predict what's on the product side. Decomposition and synthesis are a bunch easier in terms of what we're doing. We see a compound, it's getting heated or maybe hit with electricity, and that's breaking it apart. With synthesis reactions, we see a couple of elements being slammed together to make a new compound. And for both of those, you're going to have this paper that kind of gives you some examples, and you're going to have to figure out which example it matches. You're going to say like synthesis number 2 or decomposition number 4 or whatever example it matches up with. And then the fifth type of reaction that we dealt with a bunch was combustion reactions. And combustion reactions have some combination of carbon and hydrogen, could be 2 and 4 or 3 and 6 or whatever, reacting with oxygen. And depending on how much oxygen it is, you can have one of two possible answers. You could have CO and water, or if he moves the pen, CO2 and water. And the big key was how much oxygen was present. If there was plenty of oxygen, or let's say an excess of oxygen, then you have 2 oxygens attached to the carbon. If there wasn't a lot of oxygen, if it was a limited supply of oxygen, then there was only 1 oxygen attached to the carbon, not 2. All right, let's get to the answers. I know you're all excited. So here we go. I'm not going to stay on these pages very long. We should just be kind of going over, making sure we're doing things right. 1, 2, and 4. 1, 2, and 4 are definitely double replacements. We have 2 compounds. We're putting them together in their new combinations. Anytime we put a combination of elements together, we are starting off by worrying about their charges first. So when I put this magnesium and the nitrate together in the first compound, I wrote down their charges on the side, and then I said, okay, well, magnesium's a +2, and nitrate's a -1. I got to make the right compound here. I need 2 nitrates, actually. And after I did that for every compound, I then worried about balancing my reaction. That's a good abbreviation for reaction. And we balanced the reaction after we do the charges. And I came around and I put my 2's and my other coefficients in there. And then lastly, I worried about solubility or states of matter. You know, is it solid? Is it liquid? Is it gas? What is it? So I went through the solubility rules, figure out things are aqueous or solid. We'll hit a little bit more on that later. So that's what's going on with 1, 2, and 3. You put the new combinations together using their charges. You then balance the reaction, and you hit the solubility rules. On number 5, we have a wrong thing. On number 5, we have a single replacement. We can tell that because we have a compound and a single element. And so we have to test and see whether or not that single element is high enough on the activity series So I check the activity series, and since bromine is higher than iodine on the activity series for nonmetals, it can replace that iodine. And when I replace it, I have to go through these same steps down here. I replace it, I look at the charges, I then balance the reaction, I then worry about the solubility or states. Number 3 is a straight up combustion reaction. It says there's excess. I think the combustion reactions are the easiest ones to predict. I see a hydrocarbon, some combination of carbon and hydrogen. I see oxygen. There's a lot of oxygen. So it's just CO2 and water. So I put my CO2, I put my water down. Combustion means it's actually on fire. Yeah, that was a weird accent, sorry. And since it's on fire, all of those products are going to be gases. I've never seen a fire with water trickling out of the side. It comes off as steam. And then you still have to balance it also. And then number 6 was a synthesis reaction. Those two elements came together to make zinc oxide. And if you look on your synthesis sheet, it looks like synthesis number 1. But you're going to get that synthesis sheet on the test. So you just need to look at it and figure out which one to match it up with. Oh, back on, and number 6 also needed to be balanced. Those blanks aren't there just for fun. Make sure you're balancing them. 7, another synthesis. It looks like synthesis number 2. Let me go pause for a second. There we go. I just wanted to bring these things down here again. So synthesis number 2 for number 7. They came together to form a new compound, and then balanced it, and I looked at the synthesis sheet to figure out which one it looked like. Number 8, we have another double replacement. So I went through those 3 steps. What are the charges? Balance of reaction, solubility. 6 and 11 are both decompositions. Decompositions are easy to identify as decompositions because they have electricity or heat, usually breaking them apart. And again, it's one compound. Whoa, that is not what anyone wanted me to do. Kind of making you dizzy? Sorry about that. There we go. Just pen. We have one compound breaking apart into 2 pieces. So we're breaking it apart, we're decomposing it. And then you have to figure out which decomposition it matches up with. That number 11 is literally the example given on the decomposition sheet. It is an exact match for decomposition number 3, the example. Number 10 and number 12 are both single replacements. They are slightly different. In number 12, we have a metal. In number 10, we have a non-metal. And so when we go to the activity series on the back of your periodic table, there's 2 different lists. One's for metals, one's for non-metals. And so in number 12, since that's a metal, we're going to compare it to the metal that's in the compound. Kind of looks like a weird smiley face there. And then in number 10, since chlorine's a non-metal, I'm going to compare it to bromine, because bromine's the non-metal. Let's put another I in there. So with single replacements, you go to the activity series. If the element's higher, then it can replace it. And then you go through the whole charges, balancing, solubility. 13, we've got another combustion reaction. What's the difference between this combustion reaction, limited, and the one on number 3, excess? When the oxygen supply is limited, carbon monoxide changes. I mean, you make carbon monoxide here. You don't make carbon dioxide because you don't have enough oxygen. You have a limited supply. So we have to write the 2 products, carbon monoxide and water, and then balance the reaction, and then move on. And I wrote CI for incomplete combustion. 14 and 15, both double replacements. We go through all the steps, do the charges, do this, do that. We have the solubility going on over here, right? If you look at the back of your periodic table on the solubility rules, when you see something is soluble, soluble means it's dissolved in water, which is abbreviated for, we use AQ for dissolved in water. If it's insoluble, then it would not be dissolved in water, also known as solid, right? So since these two compounds are insoluble in water, we wrote their state of matter as solid. How do I know they're insoluble in water? Look at the solubility rules. Again, let me grab those 3 steps. So the 3 steps, we have charges, balancing, solubility. So when I made these compounds over here, I used their charges. I went to the periodic table. I went to my knowledge of polyatomic ions. I then balanced the reaction. And then I used the solubility rules on the back of my periodic table to figure out their states of matter, just like we've been doing for a couple days. 17, we have a single replacement. Fluorine is really high, and we have 2 decompositions. 19, we have a synthesis. It was already balanced, so I wanted to indicate it was already balanced. And let's talk about 20, because that's a fun one, he said. So iodine is on the bottom of the activity series. So if iodine is on the bottom of the activity series, it can't replace the chlorine. All right, it can't replace the chlorine. So when you drop iodine into that solution, the chlorine and the magnesium are going to stay bonded together, and the iodine is just going to be floating around in there by itself, not doing anything. We might have the same thing occur on the metals list. If you look on the metals list, there's a number of elements at the bottom of the metals activity series. But by far, the least reactive metal is this metal, Au. Gold, which is why people wear it for jewelry, because it's not reactive. So if you put gold into this solution, is gold or magnesium higher on the list? That's right, magnesium's higher on the list. So magnesium can't be replaced by the gold. And so nothing would happen if it had been gold either. All right, let's run on here. We have 21. We have to write a dissociation equation. That just means that when the solid goes into water, it would dissolve. That is assuming that the solid is soluble in water. So if we have a soluble compound that was a solid before, so this side over here is before water, this side is after water. Before it was in water, it was a solid. Now that it's in water and it's soluble, it's aqueous. It's broken apart into its ions. We could already hit 22 when we started. That was a big sigh. Sorry, guys. Talking so fast. 23, we have just what is going on in a combustion reaction. We've been breaking hydrocarbons apart. 24, how do we determine the states of matter for pretty much anything, actually. It says double displacement, but we spend a lot of, anytime we have a compound, we're using the solubility rules, assuming that it's in water. You're going to have to read through them. You're going to have to read through them, and you're going to see exceptions, like rule number 3. Chlorides are always soluble except with lead, silver, and mercury. You don't have to have these things memorized, but you do need to be able to read them. And if it's soluble, like we said a second ago, then the state of matter is aqueous. If it's insoluble, the state of matter is solid. Good job. In 25, what happens when you mix an acid and a base? So bases have hydroxide, and acids have hydrogen. And so they make water, and then they make a compound, an ionic compound, XY, whatever that ionic compound is. We usually call that ionic compound a salt, but it doesn't have to be sodium and chlorine to be a salt. That's the only salt that we eat, though. So acids and bases have hydrogen and hydroxide that are neutralizing each other. And that's the end. So you're going to get a periodic table with all the solubility rules in the activity series, and some of those funky polyatomic ions are on the back. And you're going to get the synthesis decomposition sheet. You're going to get the test. And you have the entire rest of the period to get it done. So you need to stay focused and get her done. All right, guys, good luck.